Over a period of time, Jasper has found that the probability of a patient having a particular genetic marker that he is trying to investigate is about 6%. He wants to take a sample of patients and would like to be at least 95% confident that he gets 3 or more patients with the genetic marker. What should his sample size be? So if we say that X is the random variable, the number of patients that have the genetic marker, then that is going to be binomially distributed with n in the sample, so n trials, and a probability of success of 0.06 taken from the 6%. Now, Jasper wants at least 3 patients with the marker, so we're looking at the probability of X being greater than or equal to 3, and he would like that probability to be at least 95%, so that's 0.95 as a decimal. It might well be easier to look at this by saying, well, if X is greater than or equal to 3 is greater than or equal to 0.95, then X being less than or equal to 2 would be less than or equal to 0.05. That way, we only need to look at probability of X equals 0, 1, and 2. Now, at this stage, you might think, well, there'll be something that we can do on the class pad to do with this. For example, we might decide to do a solve and put 0.05 equals, and then do an interactive and go to our binomial CDF. And we know we're looking from 0 to 2. Let's just make the number of trials an unknown. Let's put X in there. And the probability of success we know is 0.06. Unfortunately, it doesn't answer it. And there's an obvious reason in that this equation here might well not give us an integer value, but we know that the binomial is a discrete distribution. X must be an integer value. And then you might think to yourself, well, hold on a second. Let's put a greater than in there and see what happens. Unfortunately, it doesn't like that either. So we're going to have to solve this in a manual fashion. So let's go back to where we were. And we'd already discussed the fact that that means the probability X equals 0 plus the probability of X being 1 plus the probability of X being equal to 2. That has got to be less than or equal to 0.05. Now we know the probability of success is 0.06, which means the probability of failure is 0.94. So for X to be equal to 0, that means that we had no successes. That must just be 0.94 to the power n. For X to be 1, we'll have NC1 times 0.94 to the n minus 1 times 0.06. And for X equals 2, we'll have NC2 times 0.94 to the n minus 2 times 0.06 squared. And we need that to be less than or equal to 0.05. Now, NCR is n factorial over r factorial n minus r factorial. this is something you should have learnt before, but you may not remember it now because you won't have done a lot of work on it for a while. But that means that NC1 is going to be n factorial over 1 factorial n minus 1 factorial. Now that gives us n times n minus 1 factorial over n minus 1 factorial. And so NC1 is just simply n. So what we have here is 0.94 to the n plus n times 0.94 to the n minus 1 times 0.06. And then by a similar analysis as we did up here, NC2 is n minus 1 over 2. And then that's going to be multiplied by 0.94 to the n minus 2 and 0.06 squared. And we need that to be less than or equal to 0.05. And now we've got something that we can do on the class pad. So as you can see, I've typed it in, 0.05 equals. I've used equals rather than the inequality. And you can see as we go across here, I've got 0.94 to the x, and then I've got x times 0.94 to the x minus 1 times 0.06, and x times x minus 1 over 2, 0.94 to the x minus 2 times 0.06 squared. And it's given me 102.7. And we would round up. If you go down to 102, remember it has to be an integer value. If you round down to 102, you'll find that he's going to be a little bit less than 95% confident. He wants to be at least 95% confident. So we round up to 103. So that's all we need to do is just say n is equal to 103.